Nice to meet you. So there are about 25 of you. Okay, very less. So where are you all from? Are you Bangalore or from everywhere? Even from Bangalore. Mostly from Bangalore, is it? I see. Okay. Okay. So where do you study? Oh, here. Okay, you're from Bangalore. What about you? I see. Okay. I studied in Delhi long ago, but that was not there in my time. I studied partly in Delhi University first and then Jamia Millia. What about you guys? Oh, you're from here. We have time. That's why I'm getting to know you.
Christ is very close to.
Very close. Yeah, yeah. We are neighbors. Okay. What about you? All of you are from Christ. We too. Okay. Illinois. Oh, you come very far. You live in Bangalore. Okay. What about you guys? Sorry? Ashoka. Okay. You? Aisa Pune. Okay. Oh, Kolkata. Pune. Okay. Vellore. Okay. What about you? IT Kharagpur. Okay. IISc. Okay. What about you? Bhopal. Okay. Which Pilani? Okay. Which Pilani? Pilani, right? No, in Hyderabad. Okay. So you were taught by Rahul Nigam? Yeah. Okay. What about you? Aisar Pune. Okay. IIT Madras. Billai. Okay. What about you?
You said IIT Billai.
IISER TBM. Okay. Okay. I know many people in IISER TBM. All my friends are there. Okay. What about last? Narayana. Where is it? In Andhra Pradesh. Okay. Is it the same branch as the hospitals? Okay. What about you? Florida Tech. Okay. Also far. You live here. You are? From Mumbai. Okay. What about ABS Mumbai? Okay.
Rahul, can you check if the mic has battery? We will change it now. This way.
It's on, right? Mic.
Check. Doesn't say any indication. It should be fine.
The room is small. I can shout.
No, so the recording. Recording
okay.
and online, that's actually necessary.
Okay.
If needed, we can just replace the batteries.
Sure. Okay. Last few people. NIT. Okay. What you? You already said? Mumbai. Okay. Sorry, I missed that. What about you? IT Indore. Okay. Last. You're a technician. Okay. You can say RRI. Okay. Quite a widespread group. So, is this the time correct? Okay. Okay. So, let us begin. Okay. So, you have introduced yourself. So, let me introduce myself. So, you can see my name there. You can call me Prava for short. My name is very long. And I work in cosmology. So, I was given, Kartik has given me the job of summarizing background cosmology. So, you can see that I work in cosmology and I work on the fluctuations in cosmology. Okay. But what we are going to talk about mostly, he has told me to talk about background cosmology, which does not deal with fluctuations. I will try to sneak in some fluctuations towards the end. Okay. So, what is our subject? So, when you study physics, you would have said, okay, this is my physical system, and when I say I study this system, you will basically find out certain properties, right? So, what do you do? So, you have studied Newtonian mechanics, you have studied electromagnetic theory, statistical physics, thermodynamics. So, you always had a physical system, right? That is your object of interest. And you are asking various questions about it. So, let us organize the questions into maybe physical properties and time evolution dynamics. So you have the system and you do this. And also you have a space is there as the region in space where your system is placed. So you assign coordinates to give the location, and dynamics is given by saying, okay, how is the system changing as a function of time. It could be the location changing as a function of time, or it could be other properties such as energy and so on changing as a function of time. So I am starting with this because cosmology is a what is our system, right? So it can be a bewildering system to study. So we have to first know what is our system. So what do you think we study in cosmology? You have studied in the last few lectures, you had introduction to astronomy, you have had gravitational wave, GR, some introduction to GR and so on. So maybe can you relate with that and tell me what is it that I am going to study in cosmology?
The evolution of the universe.
Universe.
Beginning and evolution.
Beginning, and that is dynamics. So basically you are saying that the universe is your system, but it's a very vague thing, right? How will you write down? So when I say this, say okay, I want to study this as a system, I know what it is. I assign a mass to it, I assign energy to it, I say okay, it is located here and so on. But with the universe, how will you do that? I am just trying to make you think approach the subject so that we are able to set up these variables, okay, the variables for which we want to set up equations. So the two boys have answered, some girl maybe. That is time. I am talking about the system. So when you say universe, what comes to your mind? What is our system? Cosmic wave, okay. Okay, so I don't want to spend too much time on this. I just want to initiate our thought process. So what do? We have space, of course, all the space around us, and there is matter located in different parts of that space. And so that distribution of matter, energy, photons, whatever, dark matter, baryons, that is going to be our system. So clearly one thing you can appreciate when you connect with the undergraduate physics that you have learned is that we cannot do, it is not proper to just think of it as a compact object whose velocity I want to measure and energy I want to measure. What I am going to need is statistical physics, because I have a distribution of system of particles, what I call particles, and I am going to describe that. So what I am going to take you through is how to formulate the equations. I am going to motivate you towards the equations, and I am going to start with observations. How do we approach the studying about the universe as a whole? Okay, so I just use this slide to motivate that we are here, but then as you zoom out and zoom out and zoom out, think about larger regions in space. I am sure you've been told about various length scales. So if you zoom out to scales of about megaparsec, okay, megaparsec, which is 10 to the power 22 meters, then the galaxies and so on start looking like small compact objects. So the scale at which, when we say I study the universe, it is very difficult to think about human scale size, study physics, and also at that scale. So the physics laws, applicable laws will differ, and so when we study the universe, typically we are interested in thinking, okay, this region in space is like a point for me. There is a certain mass located in that region, in that space, and I am going to think about this as a unit of the statistical system. So there will be, you will take a large volume, each will be like a point, and this is what my system is. So this is an image from the Euclid satellite, which was started taking data very recently. This is very exciting data to look forward to. Okay, so when we study the universe, what do? I am going to take the approach of starting with experiment. So, we collect data and we see a lot of things and we organize the data that I collect, and we want to make sense of the organization. That means we want to catalog systems and so on and say, okay, this is how things are changing, evolving and so on, and for that we need the theoretical framework. But then physicists are very creative people, so they will come out with different kinds of theories, and you want to know which is the correct theory which is describing the universe, okay, what nature is selecting. So, there can be many theories, and for that you have to do data analysis. That means you compare the data that you have collected from your experiments and you compare the different kinds of theory, and you let the data tell you that this is the correct theory for us. Then when you do this process, you will encounter things that you do not understand. So, in which case again you have to go back and revisit your theory. Maybe my theory is wrong somewhere, or maybe it is valid in this length scale or in this time region, I need to revise it. So, you come up with more theory, and now as you revise your theory, you also need more data, because your theory will say, okay, this thing is I am going to see in experiment, and then you go back. So, it is a loop. So, this is how we push our frontier of our understanding. So, I am going to take you through this. So, let us start with this. So, today I hope to cover the experiments that are relevant, some key experiments that are relevant for understanding the cosmos as a whole. Okay. So, let us start by, when I say I observe the cosmos, when I say I observe you, for example, what I am effectively saying is light is bouncing from you and my eye is receiving the photon from you. So, just like that, the distances are far away. So, when I see something far away, I am basically saying that I am receiving some signal that comes from that object, and I am able to see it, and looking at that signal I can say, okay, this object is this, or it has this property. So, this is what we do. So, I am using the word for the signals that we receive, I am using the word messenger. You would have heard this, I am sure, in the previous lectures, and we have the more number of messengers you get from an object, the more deeply you will understand what that system is. Okay. So, of course, the messengers are going to be photons. So, we have the whole electromagnetic spectrum to probe, but it depends on how easy it is to construct the instruments with which we can detect the photons. So, based on that, progress has been in the way cosmology or astrophysics has developed, progress has been at varying stages. Some frequencies or electromagnetic spectrum, some parts have progressed fast, some have not progressed as fast, and so on. But our hope is that the entire electromagnetic spectrum, whatever we can see, we will be able to see. So, this is again, I put this slide to put this point across, because this is a very nice slide which was prepared by the Ice Cube collaboration, which is an experiment in the Antarctica. And what they did here, this is to demonstrate that this is the galactic center. This is our Milky Way galaxy, and we are looking at the center, and there is a black hole there, supermassive black hole. And if you look at radio frequencies, this is what it will look like. The white means very bright. And if you look at optical visible light, it will look like this. You will have all these dark spots which are like dust particles absorbing the visible light. And if you look in gamma rays, you will see this kind of emission. And what was exciting about the Ice Cube result was that for the first time they measured neutrinos coming from that region, and neutrinos, as you would have studied in your courses, they are very hard to detect, and so that is why this is exciting. So, this sort of marks a new era when, maybe I am being very hopeful, it marks an era when we will be able to use neutrino measurements from various regions to probe the cosmos. Then I know that you have also studied gravitational waves which are coming from, this is only our galactic center, but gravitational waves coming from different parts, you have studied this. And also there are cosmic rays which come from very far away, and people are very excited to know where are these cosmic rays coming from. So what am I going to focus on? Clearly this is a huge subject and huge range of topics, and I am going to focus on, for setting up the basic cosmology equations, I am going to focus on somewhere between radio and optical, so microwave photons, and I will focus on the optical to infrared, okay, in this regime. So I am going to choose these three, these and one experimental result, and I am going to use these to infer. So let us think like a detectives, let us think like detectives who are trying to solve a mystery, and we will use the evidence from the observational side from this tree, and then we will piece them together and say, okay, this is what happened. Then we will come to the theory, okay, how we set up the equations and solve them. Okay. So the the three things I am going to talk about now are the cosmic microwave background radiation. I am sure everybody has heard about it. So we will spend some time looking at the properties of that. Then secondly, we will look at the visible to infrared light, what the entire cosmos looks like, and we will discuss a little bit about the expansion of space by Hubble. Okay, so let us look at the cosmic microwave background, the CMB. So, so the CMB was first detected in the experiments were done in 1964, and the paper was published in 1965, Penzias and Wilson. So they were looking at, so in this on the x axis, let me use the plot. On the x axis is the frequency per millimeter, okay. So if you work this out in gigahertz, this will be like 160 gigahertz. So this is a range, and so Penzias and Wilson, they built a antenna in this range at around 4 gigahertz, and they were looking at signal, they were turning their antenna in different directions and collecting the microwave photons falling on it. And what they found was that there are photons coming from all directions, at least in the range. Of course, they did not do the entire sky. So they did some parts of the sky, and they found that the same signal was there on the sky. So at only one frequency they detected, so they had this number here, somewhere here, and from that they deduced that, they said, okay, I have one measurement, if I plug it into a black body radiation spectrum, what is the temperature? So they calculated what the temperature is. It was something around maybe 5 or so, or 3, I forget the number. They measured something like that, and what was surprising of that, what is surprising why microwave is being picked out is, unlike photons which in the visible range, you know, when you look at the night sky, the visible photons are coming from certain stars. They are localized, they are compact objects which are emitting, but there is some physical process in the star and the light is coming from it. Or if, yeah. 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 So, so the difference is that if you see a galaxy, have you seen any galaxy, any of you, by eye? Yes. Milky Way. Milky Way is too spread out. No, you might have seen. Any other galaxy? And have you seen it with your eye?
Like using a telescope.
Using a telescope. Okay. But do you know any galaxy which are visible by eye from Earth? Andromeda, not now. No, it's not visible. Even now with the dusty skies, if you go to southern hemisphere, you will see large Magellanic Cloud and small Magellanic Cloud with your eyes. Okay, they are visible by eye. Okay, so I was making the point that the cosmic microwave background, unlike these other frequencies, the objects which are emitting in these other frequencies, this is not localized source. It's coming from all directions. We are here, we are in the center of a sphere, and from all directions we get these photons. So, they detected that. Then the next experiment which looked for measuring the spectrum is the RASS experiment, which was on the Kobe satellite. It was sent up in around 1990, 1991, and what they did, that was a proper experiment in the sense that now they had detectors at different frequencies in these ranges, and they detected the energy for each frequency, and they got this kind of a shape. So, this is experimental data, and these error bars here are actually way 400, they have increased it to 400 times. So, this is very well measured. So, immediately when you look at this, you would think of some shape, right? What function would you fit to this? It's a black body. So, that is what you would fit. So, you so you will use you will fit the black body spectrum, and you will be able to read off a temperature, okay. And so that is what is done. So the temperature is measured from here, okay. So this is the RASS experiment. Next comes, actually I should put the Kobe experiment, but that is the resolution is poor, so I choose to show the Planck measurement, okay. Okay, now here is this plot. So let me explain what this is. What do you think this is?
Distribution of temperature.
Temperature, okay. But what is the ellipse? Where are you on the ellipse?
You pull the sides behind your.
Yes. So we are at the center, we cut it from north to south and we put. So galaxy is in this central region, and so this value is by averaging all the temperatures. So okay, when you say temperature, what we actually measure is photon, right? But you are transforming it into a temperature. So basically you are saying that okay, the whole sky together, all the photons is a black body, but in this side also, if I choose a particular direction and I do the experiment, repeat the experiment for different frequencies, I will get a temperature, and that is temperature is what is plotted here. And so the red color is slightly higher than the mean, and the mean is 2.725 Kelvin, and the blue color is slightly lower than the mean, so cooler than the mean. So this is the, so how many pixels do you think the sky is divided into in this figure? Make a guess. When we do experiment, nothing is continuous, right? So that means that I have this sphere around me, I have split it into some number of pixels. Just make a guess of how many pixels are here, just to initiate your thought process. 1,000. 1,000 you will be able to see with your eye, yeah? Gigapixels. Okay, I will tell you the answer. This is about 10 million. Yeah. 10 million. 10 to the power 7 pixels. Okay. So this is by the satellite Planck. So now given such a, you have obtained this data, we are not doing any theory, we are not talking about any theory right now, right? We are only dealing with the data. So if you are like a playful person, you will say, okay, I have all these random fluctuating numbers, what can I do with it? Or how can I play around with it? What will you do first thing?
How it will evolve after?
We don't know anything about evolution, no? I just have this data. Yeah, I can't ask that question yet. Statistical, yeah, yes?
Best fit curves, like.
Best fit curves, what curve?
Not maybe curve, like, but giving a theory, what would it be before?
I'm not doing any theory yet.
So how like the photons are distributed in the try to pick.
Okay.
How the heat is distributed among the universe.
Okay. So you will you think of it as a random variable? The temperature T at different points, I collect all of them, I have 10 to the power 7 numbers. They are random variables, right? So given that many random variables, you will do statistics with this. Somebody said statistics, I don't know who said that, raise your hand, you said. Okay. So if you do statistics, the simplest is you will find the mean. Mean you have already computed here, 2.725. Then you will calculate the standard deviation. and skewness and kurtosis and so on, right, all kinds of things you can calculate. So, or you can calculate directly the probability distribution, you can draw the histogram, and that is what is drawn here, and all these other statistical properties will follow from here. So, what we found, what people found when they measured this is that it looks like very much like this is a Gaussian distribution, and the standard deviation will be is of the order of 10 to the power minus 5. But you will say now, if you are careful about the units, when I say standard deviation 10 to the power minus 5, you have to object. I have to normalize it by the mean. I have to remove the units, right? Okay, so whatever I said just now, if you are not a theorist, you would not, we don't know what to expect, right? I just collect all the CMB photons in all the different directions, and it's not natural to think that okay, it should be Gaussian or it should be log normal or some such thing. There's no natural way to think of that. So, but we found this. So now if you think like a theorist, now you have to go back and build a theory which will give rise to that, okay? But those are fluctuations. Okay, let's summarize what we just learned about the cosmic microwave background. So the first point is we see it in all directions, they are coming from different directions. Then they follow the black body spectrum, this is experimental fact, and the average temperature is about this much, 2.725 Kelvin. Then we also saw that there are tiny differences in the temperature. So that means that I am introducing my first important equation for the theory part, and that is that n hat is a direction. In that direction, whatever temperature I measure, I can write it as the average over the entire sky plus a small change. So when I say small here, how small, how small should this be? Have you all done perturbation theory? No, some no, some yes, okay. So because, so we write like in any direction I can write like this, but of course this exact number will vary from direction to direction, no? It's a fluctuating quantity. So meaningfully what we can compare across is by looking at a standard deviation, and that standard deviation is like 10 to the power minus 5. So you can compare this with 1 because you have normalized with the mean, okay. So it's a very small number. So this is CMB. Now this is just to give you the realistic, some of you may have seen this. So this is in realistic experiments what we actually measure at different 30 gigahertz and so all up to 857. This is measured by Planck collaboration. They measure, there is a very high emission from our galactic region, and so if you are a practitioner of the trade, you will have to devise methods to correctly subtract our galactic contamination. So this is contamination, is dirtying the CMB signal. So the CMB signal, these are good, but here we have to subtract. So this is a very thriving area of research to do this correctly so that the signal is correctly obtained. Okay, so in these you can see it is completely dominated and there is no hope you will get, you will not know how much is a, I receive 1000 photons, how many is CMB, you know, is it 2 or 3, it is very hard. So this you can't do anything, but these are still useful for other regions to study the properties, how these emissions change as a function of frequency. If you know that, you can subtract. Okay, so that closes the CMB. This you may all be aware of, I think you would be knowing, you guys are very familiar these days with YouTube and all that, but just to give you the chronology, 1965 I said it was discovered, and 1978 they got the Nobel Prize. If there is any mistake in the year by 1 or 2, please forgive me, okay. Okay, then so this measured, this said the mean value of the temperature. Kobe measured the fluctuations. Kobe had about, you said 1000, no? Kobe had, because the experiment at that time was not very advanced, so they had about 1000, 7 degree. So 7 degree was 1 pixel for them. Then the next experiment, Darcy, degree, anisotropy, I forgot the full forms. So Dasi, they measured that the CMB photons are polarized. Okay, that is also exciting. So out of, if I receive 10 photons coming from this direction, they will have different directions of polarization, but some of them, a small fraction, less than 10% of them will be all aligned in the same way, linearly polarized, and that was detected. So that's very exciting. And this is actually the frontier of CMB right now, to measure the polarization very, very accurately, because there is one aspect which we have not found as yet, and that is the CMB polarization caused by gravitational waves in the early universe. So that is going to be Nobel Prize work yet to be received. Okay. Then the next two experiments, WMAP and Planck, they improved the detection better and better, which means they were technologically, they could cool the detectors very well, so that there is no contamination by stray photons from the instrument itself. So they did that. Then in the theoretical side, now because our goal is to go to the theory, in the theoretical side, the fact that the CMB photons are there, that was predicted by Gamow. I think Gamow made a mistake, and his student Alpher and Hermann, the two of them corrected, and they predicted 3-degree CMB photons. Then in 1965, when Penzias and Wilson were doing the experiment, they were designing experiments. So Decay, Peebles, and these two people, they were designing the experiment to look for them, and they came to know that these people have detected something, and then they got together and they published their, if you look in the journal, you will find their papers published next to each other. So this is the story. All right, that completes the CMB. Yeah. Yeah. Cosmic microwave background photon. Cosmic microwave, so the photon, it's a photon in the wavelength of 1-2 millimeters. How do we distinguish that? Okay, let me go here. Okay, so when you are an experimenter, you will say, okay, I look in this direction, I'll collect all the photons. But okay, you don't know, is it coming from the cosmos or is it coming from? So you will first, you will say, okay, what is the possibility that is coming from some source nearby? So like that, you think of various sources, and then you eliminate all that, and then whatever is left, you say, okay, this I cannot explain, and this is, I think, coming from the far away in the cosmos. Here's how we do. So that is your question is one of the reasons why I put this slide, because when I look in these directions, this particular direction, there is a lot of photons coming from our Milky Way. So our Milky Way, have you had a course on galaxy? No. Okay. So our Milky Way, you guys said you have seen. Milky Way is sort of planar, and we are located in one of the arms. But because we are about, I think, 8 parsec from the center, we will see emissions coming from all around. Milky Way system is enveloping us, we are inside it, right? So the Milky Way has a lot of stars. So but the stars will be very localized compact object. If they are emitting in microwave, they will be like 1 pixel here, okay, they'll have. But there is a lot of gas, okay. So the lot of gas and actually a lot of dust particles. So there's a lot of dust, you have seen in the optical wavelength dust lanes, right, the black regions in the dust. Those, they emit starlight and they emit in these frequencies, and they are a source of nuisance, and that is what we are seeing. So in these frequencies, all of this is dust emission. All of these frequencies, these are coming from, so our Milky Way, again we have a magnetic field around us, right? Maybe somebody will tell you in the galaxy course maybe. So there is a magnetic field all around us, and there are cosmic rays which are bombarding us from outer space, and those cosmic rays, they get deflected by the magnetic fields, and in the process they emit photons, and those photons are in these frequencies. So in fact it goes, here we see some, and on the lower frequency side it goes up, the number of photons goes up, and if you hear radio astronomy, which will, I don't know if you have a course, so if you do radio astronomy, you will find that that is a huge problem, like dust is here, okay. So this is how we eliminate all the sources, and then whatever is left we say is the CMB. but still of course you should keep reasonable doubt, okay, no, don't trust. Okay, so that is the story in microwave. Now let us look at optical to infrared, because this is what we are most familiar with our eyes. Of course, we discussed that whatever you see in the night sky with your eyes are stars, but you have all seen there are so many experiments now looking for galaxies and so on, and I chose this DESI, dark energy spectroscopic instrument, the latest. This is not latest actually, this is the first year release, because the image I like this better. So what they did is they just again just like the CMB, you are just pointing your instrument in different directions and collecting all the photons that come. So you measure, you are seeing galaxies. So galaxies, quasar, there are a host of different kinds of objects, but so this zoom out version is the nearby region, which is the galaxy. So you notice here that isn't this pattern, wouldn't you connect it to the CMB if you didn't know anything about theory? Just by looking at the CMB and this, would you connect it? No. Okay, let me help you connect it. Okay, so if you look at, I think the galaxy sizes are a little enlarged to make it visible, but what you notice here is that there are regions where there are lots of galaxies, they are clustered. So there is galaxy clustering, and there are regions which are empty, they are void regions, and there are also like these filamentary regions where the galaxies are aligned nicely. Okay. So how did this form? Wouldn't you ask, how did this form? Why is the structure like this? Okay, I will hold off the connection to the CMB a little later. So this is what you see, but just like what we did for a CMB, in the CMB when I want to set up my equations on my degree of freedom, I say okay, these are visible, so these are baryons. The light is coming from stars and gas and so on, so these are baryons which are emitting the light. So these are most likely electromagnetic processes which are happening, maybe hydrogen fusion and so on, those are things are happening. So what variable, if I want to describe, this is your system, I assign it to you as a system that you want to study, that means you have to set up equations for it. First, what will be your variable? Luminosity, okay, that's light. Radiation doesn't say much, but luminosity is fine. Wavelength. But I want to describe this system.
What
Density, yeah, that's what I am trying to get at. So I will set up a density, no. So I will describe, maybe I will take some volume of space and I will say that's my point, one point is that many volume, and I will say, you can say number of galaxies, I get number count. That number will vary from pixel to pixel, from region to region. So you have a variable which is, let's call it rho as a function of x. And if I see this, if I know that this is going to have evolved in time, that will be a function of t. Now given that variable, you can say, okay, in my field of view, let me average everything. So you will have a rho naught, okay, plus now in every region, whatever value you get can be written as rho naught plus a fluctuation. So this is how I will set up my variable, and I want to describe how that changes as a function of time, and it will change from place to place also. So I want to describe how it changes as a function of space. So that is the thing we observe. Yeah.
So when you say fluctuation, you mean from that rho naught, how much?
Yes, how much it differs. Yeah, from the average, how much it differs. So now you can see a problem in doing this. Well, can you foresee a problem? No, that is not. I have only given you two variables. Come on. We are going to set it up. The magic is, the wonderful thing is that the theoreticians are so good that, yeah, we can, yes. In fact, we can simulate this. Simulate means we have got the equations right, at least part of the equations right, and we are able to obtain this, right. So, that means we have progress. But what the problem I am referring to is, what is the meaning of the average? Your average, if your telescope was smaller, for example, Sloan Digital Sky Survey, it has saw a smaller region of sky, your average will change, no? So, how well defined are these averages, that is an issue in cosmology, which I will not deal with, but just keep in mind. Okay. Okay, why am I introducing the variables in this way? I am introducing because I am going to do background and fluctuation. Yeah.
If you take a small volume, how can you determine how many galaxies are there? Like,
Just count.
in the sense, how can you count? Like, there will be like millions of galaxies.
From, no, you choose a small region and you count. Based on the instrument, you will have a number.
And also, like, how can you? It's like you choose an area and call it like a local area.
Yes.
How can you determine what is it?
It is up to you to define it. Okay.
I mean,
So-
if I choose an area in which, like, if I chose like a black, where that thing is
Where
there,
not many galaxies
yeah,
are there.
I mean, that would make like my average different. a bit.
Yes, yes. So your average, yeah. So as you increase your volume, the first question, if you are a theoretician, you should ask is, if I start from here and increase, okay, the average will change. Does it asymptote? If it asymptotes at some point, then you say, okay, here it is. That is the scale. Yeah.
So you told that we can choose a local region in the sky and then count the number of galaxies.
Yes.
Sometimes, even using the best telescopes, those objects actually they may not be galaxies. They may be something.
There may be, yes, yes.
So
So there is,
how can we?
yeah, there is a lot of room for error and so on. So you have to keep improving it. So it depends on your telescope also. Your telescope, it is going to collect only very faint. If it is not able to collect very faint galaxies, you are missing those samples. So your sample, whatever you are seeing, is limited by your experimental technique.
Like the Galaxy Zoo project is still ongoing. Galaxy Zoo.
Yes, yes, yeah,
So we citizens are asked to classify
yes,
the galaxies. So
yeah,
there, sometimes it might appear as a galaxy, but it is actually not.
yes,
The data is taken using James Webb.
yes, yeah. So you appreciate the difficulty of the problem. That's why the subject is not easy, and that's why it's exciting. Okay, shall I move on from, okay, yeah, so here is the variable I just said. So we are looking at, this is called baryonic matter, even though the word baryon refers to protons and so on, hadronic. So we are going to include electrons also here, so just terminology. And the thing to observe is that in space the distribution fluctuates, and so we can write, we can assign a density, and from place to place it will fluctuate. So this rho naught will not fluctuate, and all the fluctuation is here. So we are doing this separately because we will study properties of rho naught, and then plugged in, if we do perturbation theory, we will set up our equations, zeroth order equations, solve it, plug it in first order equations, plug it in second order, and so on. But of course this is valid as long as perturbation theory is valid. Okay. So our hope is that perturbation theory is valid. Yeah.
Is this for fixed time, or like we do not consider time as like a function?
No. This time is going to come in. I did not put time here because this is measured, this is a measurement today. And I am thinking about a slice, I am assuming that they are all at the same time. Time has to be there. Yeah.
If you're calculating averages,
Hmm.
you said if you have a smaller one, it will be an issue. But overall, universe is homogeneous and isotropic. So why would a smaller?
Well, it is a matter of testing whether universe is homogeneous and isotropic. Okay. It is not a given.
Okay.
What a large scale it is to be, but
It is being tested. We'll talk more about that. Yeah.
So ma'am, if the universe is homogeneous and
Isotropic.
isotropic, so we should get a asymptotic mean graph, which is what you are telling.
If it is homogeneous and isotropic beyond a certain scale, your average will flatten out after that scale. I am averaging over 100 parsec, 200 parsec, 400. So if 100 is my scale at which homogeneity in isotropy is correct, then the mean will flatten out, otherwise it will change. That is what I am saying. This is just maths. Yeah, shall I move on now? Okay, so your question about time is going to come, and I didn't put it just because it is. Okay, just to give you a flavor of the history part. So this is today, we are seeing this. This is what Hubble had got in 1934. So Hubble looked at, I think this was around 5,000 galaxies at that time. They call it nebula at that time. So he basically, this would be like the starting point of whether it is a homogeneous and isotropic. And so this is again the sky is the galactic region, and these are all different kinds of, the different shapes are, he classified them into different kinds of objects, and he is basically testing how are they distributed in space around us. Okay. So we have come from here to here in 90 years. Okay, so the third point, experimental fact that we want to look at is this expansion of space. This is a consequence interpretation, and this is the data. So let's examine the data. So have you worked this out in the astronomy? No. Okay, so this is Hubble in 1929. This was a few years. I don't know how he went from, so here the number of the galaxies here is 22, and he had a sample of like 40, 45. This is 2019, 29. In 1934, he had like 5,000 galaxies. Okay, so he was, it looks like he was working very hard, and he was actually looking at all the photographic plate. Those days it was all photographic plate. So he looking at them by eye and then doing all the error correction. So he had these, and so what he did was he measured the distance for each galaxy, for each object, how far is it, and that distance is measured by looking at the, there are this, in astronomy class you would have learnt about Cepheid variable stars. So they have a relationship between the variability and how bright it is. So by looking at that you can say it is at this distance with the flux. So the distance is measured, then he measured the velocity. So he measured the spectra, okay, and the spectrum, they are all redshifted, and but the redshift amount depends on how far it is. Okay, so from that he got the velocity. So this velocity measurement was not his idea first. It was another guy called Slipher in 1912 who first did measuring the velocity and finding that, oh, things are redshifted, galaxies are moving away from us. So these two he measured, and he just plotted them on this velocity and distance plot, and the points are like this. So he then fit a straight line to it, and from there he can read off the slope, this line, the slope. Okay. There are two lines because he was trying to segregate the sample into two parts based on how much error is there and so on, and I think he had a number like 500 was the unit. So the unit for that proportionality constant is kilometer per second per megaparsec. Yeah. So that is the thing, and so but in his paper, in that paper, you will see this sentence written, which is that what is outstanding about this is the possibility that velocity distance relation may represent a de Sitter effect. Okay. So the de Sitter, so when we come to the theory part, de Sitter solved one of the Einstein equations with the vacuum. There is no matter, and he solved Einstein equation, and he got an expanding the phase that the universe should be expanding. And so he related it to this, and this is what makes it outstanding. Okay. And so which means that he is interpreting this relation as being due to the region between this galaxy and us, intervening space expanding, not because I am moving towards it or I am moving away from it, or the galaxy is moving with the velocity away from it, but nothing, where the galaxy is there, I am here, but the space between it has changed. So this is the expansion of space. So now if we think of the expansion of space, if this is to be interpreted as expansion of space, then we have to introduce a factor, the expansion factor A. So I am introducing the variables one by one. So I have a scale factor, we call it scale factor, A is the symbol, and the Hubble parameter H, which is A dot by A. Okay, so if we think that the space is expanding, then it is very, very straightforward to derive a relation which explains the plot. Okay, and that is that at some initial time, so this picture is depicting time is flowing this way, and this is some disk region space where there are 3 objects, and as time passes the distance between the objects increase. So tell me something you notice about the increase. Circle has increased, yes. What else? The object remains the same, yes, object remains same, circle. So circle or disk has increased, but beyond that, uniform. What do you mean by uniform?
Like there is no a center of expansion. It feels like it expands like from every region.
Can you make it more precise?
It's like
Isotropic.
It is happening isotropic expansion, but how will you make that precise? I suppose you say isotropic, yes, good, but I want to write an equation to capture that isotropy. How will you write it?
Expansion is directly proportional.
You are thinking much more complicated way, very simple. Look at this. If it is isotropic, you have 3 dots, distance between these 2 dots, that is a scalar quantity. It has increased here. This 2 also has a ratio, has a distance, that should be the same. If they are not the same, this will become an ellipse, right. So, and there will be some preferred direction where the increase is more, in which case the expansion factor only 1 is not enough, right. You will have to choose direction, in this direction this is this much, in this direction is this much, that becomes anisotropic expansion. So here in those days it was too complicated to think of anisotropic, so let us just simplify with isotropic. So the idea is that it is isotropic expansion, and so there is only one parameter, and this r could be any distance between any of them. If not, you would have to write this as a vector equation, which one is which. So in that case, so r1 we keep fixed, r1 is, so we will call it co-moving coordinate. Okay. R1 is the distance in co-moving coordinate, co-moving, the word co-moving I am introducing. Then at any later time, if it is expansion, or any time in the past, which means I go this way, it will be smaller, then that information, distance between them is captured in A as a function of time. So at any time in the past or the future, if I measure the distance between any of those 2 points, it will be contained in A, the scale factor. So then from here you just take derivative with respect to time, left hand side is the physical distance, and you get dA by dt, and you introduce A, and you get A dot by A, and you have the original, sorry I changed this to D, okay. This should be R, D or R, yeah. So this it is a natural consequence. If you think that the distance between galaxies are increasing in this way, homogeneous way, isotropic way, then this becomes, because those 200 galaxies, they were not all in the same direction, they were all in different directions. So this is the thing. Now just to open up our minds, we have just right now we did not say anything about what is the functional form of A, but we would be curious, right. If you are a theoretical, if you want to explain things from theory, you would want to know what is the functional form of A. So right now at this stage we do not have enough information to know more about it, but in general I would say A cannot be 0. Right, A is a quantity which as a function of time, if it goes to 0, that means the concept of the size disappears. Yeah.
If it is 0, then that means it is been prime. So time of
it is a singularity. So, but that is not a well defined A. No, why should it be? Right now I do not have enough information to say anything about A. We need information, yeah.
That's what I was asking. A is increasing in a ratio.
Yeah.
What ratio it is following is what I was supposed
A is increasing in ratio. A is not increasing in ratio. What does that mean?
Like it's maintaining the same ratio, but it is increasing. Right?
You mean this one?
Yeah.
So, but it depends on what value H naught is, no?
H naught is also not constant. It is also
Well, Hubble measured it with those galaxies and he got one number. So, from that you cannot say what is the functional form. A function is as a function of time, you need more degrees of freedom. Right now I have 1 degree of freedom. So, it is not enough information. Yeah, somebody said something? Okay. So, but we would like to know, no, does it change as a function of time? Yeah.
H naught was measured at what time?
He is measuring it today in 1934.
19. So that value.
Maybe it has changed slightly now in 90 years.
because the extension of the universe is not uniform. It's not going to stay constant.
It won't stay constant, yeah. Yeah, but in 90 years, will it be measurable?
It is not visible.
It will be like 0.0000, I don't know how many zeros. Maybe it's a good exercise for you to calculate. Okay, may I continue? Okay. Okay, so we need more information, but just keep your options open that A, we want to know A is a function of time. If it's like linear, as A is proportional to T, it's linear. It could be if T to the power n with n greater than 1, then that is accelerating. If you take
Also, it's the future of the universe, right? If A is linear to T, then the ending of the universe might be T dot.
well, right now we don't have any information about that. Okay, so we are going to learn more about that. And so, of interest will be well, all the classes of functions. A, what kind of functions can it be? It can be linear, or it can be accelerating, or it can be decelerating. All classes are exhausted in these three. All possible functions fall in these three categories. So we will want to know more about these later. Okay. So that is the expansion. Now a consequence of the expansion, cosmological expansion, is the redshift that was measured by Slipher and also by Hubble. So if the galaxy is moving away from us, its wavelength starting from the emitted, what we observe will be different, and that is the redshift. It will be, because it is moving away from us, it will be redshifted. If it is contracting universe, then it will be blue shifted. So now I introduce the symbol Z, the redshift, which will be very used all the time later. And so we can, lambda observed is a experimentally observed quantity. Lambda emit is, we have to make some assumptions about, theoretical assumptions of what the object I am measuring is, and we have to assume something about it to know lambda emit. And so we can relate lambda to the 1 plus z to the wavelengths, and so now we can relate A, the scale factor, to the wavelength. So we get 1 plus z is A at the time of observation, scale factor value at the time of observation to scale factor at the time of emission. So I will come back to this when we do the theory from the GR side. Okay. So this is the relation between the expansion factor and the redshift. Okay, so I told you that I will discuss 3 observational facts that we have seen, and we have collected all our clues, various clues we have collected, and now it is time to put them together. But before that, there are also stuff that we do not see, but we feel their gravity, and this I am sure must have been covered in a previous, was it covered in one of the lectures?
Dark matter and dark energy was not covered, but we know.
Okay, you know this. Okay, so this is a galaxy, and we when you look at the rotation curves of various stars and gas which are very far away from the center of the galaxy, you measure their velocities, then we find that their velocities do not just go what we expect from balancing centrifugal to gravitational attraction. This is the expected form, but what we see is this. And so there is something that we are not seeing which is affecting gravitational.
The stars mean the galactic center is moving as the same speed as stars with
Yeah, basically this part. Well, this is for this particular galaxy it is still increasing. So the dark matter is far away. So this is also there. So now let us organize our questions. I will just have a glass of water. Okay, so let us, this is my list of questions. If you have your list of questions, tell me, okay. Let me go through my list first because I am the lecturer. Okay, so we want to know, so of course the first question, why is the universe expanding, right? It is in Newtonian physics we do not encounter it. It does not say, space has nothing to do with motion, movement and change. Space is just a stage where we move around. Yeah. So why is it expanding? What is the rate of expansion? How does it change with time? All these questions we want to ask. Then what created the CMB light? Where is it coming from? Okay. Why is it so uniform? No, why the temperature is so? So here at this point I want to mention that in statistical physics you learn that if you put things together in like a box and you just let it be, over time it will equilibrate and you will have one temperature. So now in the case of CMB, I am here, I am measuring CMB in this direction, I am measuring CMB in this direction, 180 degrees apart. And I get the same, I mean 2.10 to the power minus 5 disagreement, I get the same value.
That's because it happened everywhere.
What do you mean by that?
Like the expansion of the person which has it, right? Expansion of the universe is not is going to, like if it is like a balloon blowing off a balloon, it is not expanding from one side.
That does not explain.
It is expanding everything. So it is like a cone evolving.
Okay.
So when you go back, so it has to be the same history everywhere.
Okay, very good. But do we have enough time to go back to a time when they were together? They should have been close to each other and interacting to have the same temperature, this direction and this direction. Now, light travels at finite speed. That is the fundamental limit. It's not information barrier. Don't use fancy words. Yeah.
We get called inflation and something like made the expansion steady, like that inflation that went down at like the universe grew extremely large in a very short time and then something like made that flow steady.
So that is the now currently most popular explanation. Okay, but it's not proven by theory, but yes, the inflation, the idea of inflation is developed to explain why these could have been in causal contact in the past. But at our stage, I have only seen those observations and I am building the theory. At this stage, it is a puzzle for me, right? Okay, it's a puzzle why they should be. Then the second question is, what is the statistical nature of those fluctuations, the CMB fluctuations? I said that I plotted the histogram and I found it to be Gaussian, but there is some error bar, no, there? I didn't plot it, but there is error bar, and within that error bar it can be still, so also if it is Gaussian, what is it that happened in the past that made it Gaussian? What do you think it will be? Take out your creative juices.
Like it is random things align themselves to form a.
Well, that is not a satisfactory answer at all. Random things align, it's very vague.
No, like if you burst a balloon, so the particles inside the balloon will spread among the open air. It will be, if you take each particle's data and you plot, it will be a bell curve.
What does that mean? Okay, we'll discuss it after the, let me just finish, okay, because this looks like a long discussion. Okay, so then what happened at different epochs of the universe? This is what we want to know. Then for the matter, I want to know how is the matter distributed in space? How did it evolve? Again, what is the statistical nature? You will come, this statistical nature will, you will keep hitting it when you, it will keep coming to you when you read more research level papers. Then we also want to know what are the composition of the universe, what all things are out there. I did not talk about dark energy, but it is also supposed to be there. We will discuss this next. And how much of each is present? So these are the questions, and what are the interactions between them? So we know we have studied all 4 fundamental forces of nature. That is what is going to be impacting here. On the large scales, mostly it is gravity. But when you look at local stars and so on, the other forces will become important. And so this is what we want to know. So now before we go to the full theory of GR and all that, let us, all the evidence that we have got so far from the experiments, let's piece them together and see how far we can go in understanding the universe. Okay? Okay, so here is a simulation by Volker Springel of, this is now and this is the past. So from the past, so if you look at how matter is distributed, this is actually dark matter distribution and some galaxies. The yellows are the galactic baryonic matter. Most of the hazy stuff is dark matter. Okay. So what is it depicting? This rho can be either dark matter or baryonic matter. So if I put an I index, I equal to 1 will be dark matter and so on. So for each one, what we see, just purely based on gravity, if I start at some initial time with a distribution of this type. So this box is the universe today, and I sprinkle some dark matter particles and some baryonic particles, and I let it be. And the box is expanding. Okay. So what do you expect to see? Remember that there is gravity. Gravity pulls things together. So in these regions where there is more white, higher density, things will get attracted to those. So those points, the very bright points here will become brighter and sharper. That's what you are seeing. The other thing is, in this region where there are slightly lower density, material from there will get pulled away, no, to the high density, and they will become darker, no, they will become more empty, and that's what you are seeing. So this is the effect of gravity. What do you have to do? You have to consider how the matter evolves in an expanding universe, in the box. So the only difference between doing this experiment without expansion and with expansion is expansion will delay the clustering, right, because things are moving away, so you have to move more you have to be pulled more to cluster. Yeah.
Are we taking into account the interactions between the matter?
Between the metric?
No, between the matter itself.
Matter, yeah, only gravity is being used here, only gravity. This simulation is only gravity. Okay, so this is what we expect. Now what is happening to the CMB photon? So we are starting from here and we are going backwards. So yeah. In that case, you will see it this way. Large scale for structure formation, it will be a competition between the expansion and the gravitational clustering.
Say a universe is contracting.
Yes.
Then also the structure will form.
It will form, yeah. But you can think of it this way. Or if you started from this, you will see them contracting, becoming more uniform this way. I am using the word uniform because this is more the sharp fluctuations are very high here.
Say it is contracting.
Yeah.
Also like you have some anisotropy.
Yes. Yeah.
That anisotropy will cause the matter around it to come together and go away from regions of low density.
Yeah.
So then also large crystal formation should take place, right?
Yes. That is why I am saying go backward in this direction.
If it's going backward, then these filament structures are not forming.
Filaments will not form, yeah. If you start with this initial condition, no, filaments will still form, the gravitational clustering will still happen, but it will be quickened.
So filaments will form.
Yeah. But it depends on what are the rates, maybe things will collapse faster. That's why A as a function of T is very important, yeah.
Could there be expansion such that it faster or anything that won't allow for that?
Well, as a theoretician, yes, I can think of many. If I think of the accelerated expansion, the exponential form, A as a function of T is very accelerated, then it will be, yeah.
If we have to find the function of A
Hmm.
as T, like it has to do opposite to the dark energy, right? Because dark energy is trying to expand the universe.
I haven't said anything about dark energy, yes.
But dark matter is trying to make it closer, like it's pushing the galaxy to make
No.
it constant speeds. Right?
Okay, so we'll deal with that, your question more when we do the theory, okay. So it depends on the distribution. So if it is homogeneous isotropic distribution, even if it is dark matter, it can expand, it leads to expansion.
But dark matter is meant to bound the matter itself.
In the nearby regions, because of gravitational pull, they will cluster, yes. But if the matter is distributed in a way which is homogeneous and isotropic, the whole space will still expand. Yeah. Okay, shall I move on from here? Okay, so this is a picture. Now in the meantime, what is happening to CMB? Okay, so what is the origin of large scale structure and CMB? The word for the structure we saw is large scale structure, okay, on big scales. Okay, so we have enough information to say something about the gravity, matter, how it is clustering, and the CMB photons, what is happening to them. So in the expanding space, photons will lose energy. The redshift is, the wavelength gets stretched and it loses energy, and gravity is clustering. So CMB photons will become cooler and cooler as time passes. So in the past it will be like this and it will become cooler. So in GR, energy, the conservation is not just of energy, its energy momentum together is conserved. So it gets transferred into other maybe in the expansion of space. Okay, so we have enough information to say that the universe was denser, it should have been hotter in the past, and this is how it is. But now when we do the 3D theory, we want to know exactly when what happened. No, we want to predict these. Should at this time age it was this temperature. All those things we want to predict. So for that we need to do the theoretical. So this problem was tackled first time by Tolman in 1934. So now a little bit brief epoch of recombination. So if I keep going back in the past, I know that there should have been a time when the CMB photons were very energetic, right? Today it is 2.7 Kelvin, but in the past it will become hotter and hotter, and at some point it will have 13.6 electron volts as a mean temperature. At that time you can calculate what would be the temperature of the CMB black body spectrum. That's like 50 Kelvin, 50,000 Kelvin. So based on 13.6. Then at that time you know that they have enough energy to split. If there is hydrogen atom, they have enough energy to split the hydrogen atom. And this is not the CMB decoupling temperature. Okay, it is lower. I'll discuss that tomorrow. So what happened in the past would have been, so the gravitational, so matter, the clustering would be less and less in the past, so they will be distributed. So at some point I would expect the universe to be mostly hydrogen, all this box will be full of hydrogen. In the meantime, the photons are getting hotter and hotter, time is this way, so we come this way, and these are hydrogen atoms, this picture is showing. And at some point they are going to be energetic enough to split the hydrogen, so it will be in the form of this plasma. So there will be free particles, electrons and protons will be free particles, and we expect that this should have been staged in the early universe. Okay. So, the time when the last scattering between photon and the hydrogen atom happened, that is usually called the last scattering time. The word surface is used, but it's strictly speaking is not just a surface, but it lasted over some period of time. So, that is the last scattering, and so that marks a transition when photons were free, they just travel freely, to the past when it kept bouncing from electron to electron and splitting hydrogen. So, the mean free part was very short here, and here mean free part is very large, higher than the age of the universe. Okay, so that is the, is there anything? Okay, so this is a good place to end, I think, the first lecture. So, next, this is what we will do next, the theory part. Okay, so now, yeah, I will take questions. Oh, what caused the Gaussian? Okay. So, again that is a question about the fluctuations, right? You are asking about the CMB, why is it Gaussian?
Yeah, you asked that.
Okay, sorry, I asked. Okay, why is it Gaussian? I would like to start with you guessing why is it Gaussian. Then I will tell you more. So, this is what you are looking, the question is about this, yeah.
Is it because like large number of samples?
Okay, central limit theorem.
It is the randomness, right?
It is the randomness. You are very sure.
If you are dealing with some box, some gas particles are inside, sometime in later it would show that those particles will have highest form of their energies.
Okay, as an exercise, go back and read the statement of the central limit theorem very carefully and come tomorrow. Okay, central limit theorem, what does it say? Does it apply here? We will discuss that. Okay, but don't be too sure. Huh? Oh, I see. Okay, I just want to finish the, so the question of why this is looking Gaussian is connected to what created the fluctuations. Okay, how did the fluctuations arise in the first place? So, the current theory which says that inflation, that in the early stage of the universe there was a period of inflation, which means accelerated expansion. Now, when you say accelerated expansion, you want to know what matter, what kind of matter is causing that expansion. And the current theory, I won't call it fully theory, current accepted model is that there was the universe, what we need to describe the universe at that time is quantum field theory on curved space-time, because this is curved space-time and quantum field. So, there was a quantum field which is a scalar field, and that scalar field has quantum fluctuations. Okay. So, the quantum fluctuation is a natural process in quantum field theory. Okay. And that quantum fluctuation, when the space becomes larger, it will get frozen, there will not be anything quantum. So, the universe will be born in such a way that in this region there will be a little bit more matter, here there will be a little bit less, and here there will be a little bit less, more, and so on. So, this is the fluctuation. Okay, this is how it is born. Wait. Then you look at the quantum field theory of the scalar field, what is driving this. So, when you work that out, you will find you can model it from the comparing with the data, you can model it as a free field. Okay. A free quantum field, the fluctuations are Gaussian. Okay. And that is related to why it is Gaussian. However, because the field, the quantum field was interacting with gravity, it is not really a free field, right? It is a quantum field on a curved space-time. There has to be some interaction. First point. Second point is it has to, the scalar field we do not see today, right? There is Higgs, but it is with great difficulty we saw it in CERN. It is not like we can detect Higgs particles in real life, it is not there. So, if early universe during inflation, it was the scalar field particles were present, they should have all decayed into the standard model particles that we are made of. Okay? That means that there has to be interaction. So, the interaction, there are two kinds of interactions I am talking about. These interactions will mean that the scalar field we are talking about cannot actually be a free field. Okay. So, there has to be some deviation from this Gaussian shape, which because of our limitation in measurement and drawing, maybe it is very small, and so it is very small, but it has to be there. And that is why this is a very, very exciting area of research, to calculate both from the theory side, what are the interactions like. Okay, you plug it into Lagrangian, you put the and then you work out what are the interaction terms and what deviation from Gaussian behavior, what will it look like. So, we theory people calculate that. From the observed data, in the observed data, we need to measure the data to very high precision to find whether there is any deviation from, when I make a plot like this, if I am to claim that it is non-Gaussian, it is not Gaussian, slight deviation is there, that for that I need very high precision data, and Planck data is not good enough for that kind of precision. To the precision they are capable of, they say it is Gaussian. So, now there are experiments which are already on way. For example, Simon's observatory is already collecting data, and we will have better, the errors will shrink, and we will hear more about this, and I think they will start giving data in a year or two. So, we will start hearing more about it. Okay. So, the answer to your question is, because the field, it is telling that if inflation is correct, what kind of interactions it had. The interactions were very weak, that is what this is telling. This is data, we have to take the data and say something about the theory. So, this is what it is telling us. And different interactions will lead to different deviations. Is it skewed? No. Is the peak shifted like this, or is it like a kurtosis, no, symmetric but very broad? Those kind of detail will tell us about what are the interaction terms present in the for the scalar field interaction with other particles. So, that is the answer. I hope I have answered your question. Okay. Okay. So, Karthik says we should go for tea. It is better. Okay. I don't know, I leave it to them. This is also informal. Yeah. No, there's nothing natural. What about log normal?